Every AI you've used today runs on neural networks, but here's what nobody tells you. There are 10 core architectures that power literally everything, from ChatGPT to Face ID to self-driving cars, and most of them were invented decades ago by researchers who never saw their ideas change the world. I'm breaking down all 10 types, ranked from least to most interesting, and trust me, the last one runs a $300 billion company, starting with a military invention that almost nobody remembers. Radial basis, functions. Most neural networks take forever to train because they use backpropagation. But in 1988, British defense scientists at the Royal Signals and Radar Establishment needed pattern recognition that trained in seconds, not hours. So they built something completely different. Radial basis function networks use 3 layers, but the hidden layer works nothing like standard neural nets. Each neuron stores a center point and only activates when input data gets close to it, like a radar detector tuned to one specific frequency. Training happens in 2 lightning-fast steps. Use k-means clustering to position the neurons, then solve one simple linear equation for the output weights. Done. Here's the cool part. If all the neurons output near 0, the network is basically saying it doesn't know the answer. GPT-4 can't do that. It'll confidently make something up. RBFNs just stay quiet when they're uncertain. The architecture even mirrors your biology. The neurons in your inner ear are locally tuned to narrow frequency bands, exactly like RBF neurons, but the math kills them in high dimensions. They can't go deep, they can't scale, and they've been almost completely replaced by architectures that sacrifice speed for power. They still run some control systems and robotics, but most AI engineers have never written an RBF network in their lives, which brings us to something even more forgotten, a network that draws its own maps, self-organizing maps. In 1982, a Finnish computer scientist named Teuvo Kohonen invented a neural network that does something wild. Feed it 50-dimensional data about countries, economies, demographics, whatever, and it automatically compresses everything down to a 2-dimensional color-coded map, where similar things cluster together. No supervision, no labels. The network just figures out the structure on its own. Here's how it works. You start with a grid of neurons, maybe 10 by 10. Each neuron has a weight vector. When you feed in data, the neurons compete to see which one matches closest. The winner and its neighbors all adjust their weights to become more similar to that input. Over thousands of iterations, the learning rate shrinks, the neighborhood radius contracts, and the map organizes itself. Your brain does exactly this. The somatosensory cortex has a distorted body map called the cortical homunculus. Your lips and hands get massive brain real estate because they're more sensitive. Your back gets a tiny sliver. Self-organizing maps create the exact same distorted but faithful representation of whatever data you throw at them. The peak achievement was the WebSOMON project in the late 1990s. Kohonen's team organized over 7 million patent abstracts into a searchable visual map using more than 1 million neurons, processing 43,000 dimensional vectors. This was Google Maps for knowledge, years before Google Scholar existed. Kohonen also built the phonetic typewriter in the late 1980s, converting spoken Finnish and Japanese to text using self-organizing maps. The man went from measuring positron lifetimes in quantum physics to creating unsupervised learning algorithms that discover hidden patterns in any dataset. He's the most cited Finnish scientist of all time, generating nearly 8,000 academic papers. He died in December 2021 at 87. Today, SOMs are mostly replaced by TSNE and UMAP for visualization, but they still run in finance, bioinformatics, and oil exploration. At least they're still used somewhere, unlike the architecture that promised AI memory but mathematically couldn't deliver. Recurrent neural networks. Every neural network we've covered processes inputs independently. Show it a cat, it sees a cat. Show it a dog, it sees a dog. But what if order matters? What if you need to process a sentence where the meaning of each word depends on everything that came before it? That's why recurrent neural networks were invented. In 1986, Michael Jordan introduced recurrent architectures, and Jeffrey Ellman published the influential Ellman network in 1990. The breakthrough was simple but revolutionary. The network feeds its own output back into itself at the next time step, maintaining a hidden state that acts as memory. The math is elegant. At each time step, the network takes the new input and its own previous hidden state, combines them through weighted connections, and produces an output plus an updated hidden state. The same weights are shared across all time steps, making the architecture incredibly parameter efficient. But here's where it gets dark. Training uses backpropagation through time, which unrolls the network across every time step. Process a 100-word sentence, and you're effectively training a 100-layer deep network. The gradient gets multiplied by the same weight matrix at each step. If the largest eigenvalue of that matrix is less than 1, the gradients shrink exponentially. Multiply 0.5 by itself 100 times, and you get approximately 10 to the negative 30th power. Your gradient is basically nothing. This is the vanishing gradient problem, formally identified by Sepp Hochreiter in his 1991 diploma thesis. Vanilla RNNs can only remember about 10 to 20 time steps back. That's it. Try to learn longer longer dependencies, and the gradient vanishes into mathematical oblivion. In 1993, an RNN-based neural history compressor solved a task requiring over 1,000 unfolded layers, 2 decades before deep learning became a buzzword. But the gradient problem made RNNs unreliable for real applications. Today, vanilla RNNs are essentially obsolete, completely superseded by LSTMs, GRUs, and transformers. But if you think vanishing gradients killed neural networks, wait until you hear about the architecture that used 19th century physics equations to bring them back from the dead, Boltzmann machines. Most neural networks learn by adjusting weights through gradient descent. Boltzmann machines do something completely different. They use equations from 19th century thermodynamics to learn probability distributions. The network defines an energy function over all possible states, and lower energy means higher probability, pulled straight from statistical physics. The practically useful version is the restricted Boltzmann machine. 2 layers, visible and hidden, with connections only between layers, never within. Training uses contrastive divergence, where the network heats up to explore possibilities and cools down to settle on answers, literally mimicking how blacksmiths anneal metal. Here's the insane part. These networks are named after Ludwig Boltzmann, an Austrian physicist whose statistical mechanics equations power the architecture. His peers ridiculed him. The scientific community rejected the existence of atoms. Boltzmann died by suicide in 1906, nearly 80 years before his equations would revolutionize artificial intelligence. In 2006, Geoffrey Hinton published a paper called A Fast Learning Algorithm for Deep Belief Nets. He showed that stacking restricted Boltzmann machines layer by layer could train deep networks effectively. This single paper is widely credited with ending the AE winter and reigniting the deep learning revolution after decades of stagnation. The technique solved the deep network initialization problem that had stumped researchers for 20 years. RBMs powered Netflix's recommendation system during the Netflix prize competition. The architecture proved that you could stack simple components into something powerful, setting the stage for every deep network that came after. And here's the kicker. Geoffrey Hinton, who built Boltzmann machines on Ludwig Boltzmann's equations, won the 2024 Nobel Prize in Physics for foundational contributions to machine learning. The godfather of AI won a Nobel for using century-old physics to create modern intelligence. The original restricted Boltzmann machine was called Harmonium when Paul Smolensky introduced it in 1986, named after the musical instrument. The name didn't stick, but the math did, creating a direct lineage from Boltzmann machines to deep belief networks to VAEs to GANs to modern diffusion models. Today, RBMs are taught in every machine learning curriculum as the conceptual bridge between physics and AI. But if you want the architecture that actually powers everything, we need to talk about the simplest neural network ever invented. Feed-forward neural networks. This is the architecture behind everything. Every transformer, every CNN, every GAN, every diffusion model contains feed-forward layers at its core. Information flows in one direction only, from input through hidden layers to output, with no loops or feedback. Each neuron computes a weighted sum of its inputs, adds a bias, and passes the result through a nonlinear activation function. In 1989, George Cybenko and Kurt Hornick independently proved the universal approximation theorem. A single hidden layer with enough neurons can approximate any continuous function to arbitrary precision. This is the mathematical proof that neural networks can theoretically learn anything. The theorem says nothing about how to find the right weights, but it proves the power is there. But here's the story nobody tells you. In 1958, Frank Rosenblatt built the Mark I perceptron at Cornell, a 5-ton room-sized machine that learned to distinguish left from right after 50 tries. The New York Times called it an embryo of an electronic brain that would walk, talk, see, write, and reproduce itself. Rosenblatt became a celebrity scientist overnight. Then in 1969, Marvin Minsky and Seymour Papert published Perceptrons, a book proving that single-layer networks couldn't solve XOR, a simple logical operation. The book was interpreted as killing the entire field. Funding evaporated worldwide. Neural network research was considered a dead end. The AI winter lasted over 15 years. Frank Rosenblatt drowned on his 43rd birthday, July 11, 1971. He never saw his ideas vindicated. In 1986, Rumelhart, Hinton, and Williams popularized backpropagation, proving that multi-layer networks could learn anything. Neural networks roared back to life. The Marquis perceptron now sits in the Smithsonian Institution. The IEE named its highest neural network honor the Frank Rosenblatt Award in 2004. One book review killed an entire field of science for 15 years. Today, the perceptron's direct descendants power a multi-trillion-dollar industry, and feed-forward networks still dominate in 2025. Google Brain's MLP Mixer in 2021 showed that pure feed-forward architectures with no convolutions and no attention could rival vision transformers on ImageNet. The feed-forward layers inside GPT-4 function as key-value memories storing factual knowledge. The simplest architecture is still the most fundamental, but if you want to see what happens when you force a feed-forward network to compress data through a bottleneck, you get something that can read AI's mind. Autoencoders, a neural network trained to copy its input to its output, sounds useless, but force it through a compressed bottleneck in the middle and something magical happens. The encoder squeezes data into a compact representation. The decoder reconstructs the original from this compressed code. The network learns the most essential features of the data without any labels. The breakthrough variance changed everything. In 2013, Diederik Kingma and Max Welling introduced variational autoencoders. Instead of a fixed bottleneck, VAEs use a probability distribution, creating a smooth, continuous space where you can generate entirely new data by sampling. VAEs are a core component of Stable Diffusion. The VAE compresses 512 by 512 images down to 64 by 64 latent representations, a 48 times compression. The diffusion process happened in this compressed space, making it computationally feasible to run on consumer hardware. Without the VAE, Stable Diffusion couldn't run on your gaming PC. But here's where it gets absolutely wild. Sparse autoencoders are the hottest tool in AI safety right now. In 2024, Anthropic used sparse autoencoders to decompose Claude 3 Sonnet's internal activations into approximately 260,000 interpretable features. They found neurons corresponding to specific concepts: the Golden Gate Bridge, neuroscience research, deception. Then they amplified the Golden Gate Bridge feature to 10 times normal strength. Claude became obsessed with the bridge. It dropped references into every response. When asked to write code, it added comments about the Golden Gate Bridge. When asked about itself, it eventually claimed it was the Golden Gate Bridge. Golden Gate Claude became a viral meme. OpenAI followed by training a 16 million feature sparse autoencoder on GPT-4. The research found something even crazier. One part of Claude stores the fact that bananas are yellow. A completely different part evaluates whether that statement is true. The model separates factual knowledge from truth assessment, which explains why AI sometimes knows something but still gets it wrong. Researchers call this approach the alien autopsy. Autoencoders trace back to Rumelhart, Hinton, and Williams in 1986. Hinton revived deep autoencoders in a landmark 2006 science paper. Beyond generation, they power anomaly detection and fraud prevention, drug discovery through molecular interpolation, and medical image denoising. From simple data compression to reading AI's mind, autoencoders evolved into one of the most versatile architectures in modern AI. But if you think training a network to compress data is clever, wait until you hear about the architecture that was invented at a bar and solved a problem researchers thought was impossible. Long short-term memory. Recurrent neural networks promised to give AI memory, but the vanishing gradient problem destroyed that dream. Multiply the same weight matrix across 100 time steps and your gradient decays to nothing. Standard RNNs can only remember 10 to 20 steps back before forgetting everything. In 1997, Sepp Hochreiter and Jürgen Schmidhuber published long short-term memory at a small Austrian university during the AA winter. The paper introduced a gating mechanism that completely solved the gradient problem. Think of the cell state as a factory conveyor belt. 3 workers control everything. The forget gate decides what to throw off the belt. The input gate decides what to add. The output gate decides what to show the boss. The critical insight is that the cell state update is additive, not multiplicative. So gradients don't decay through repeated multiplication. This constant error carousel lets LSTMs remember over 1,000 time steps. Initial reception was lukewarm. The paper got barely 10 to 20 citations per year for the first decade. Today it has over 70,000 citations, making it the most cited neural network paper of the 20th century. The forget gate wasn't even in the original design. Felix Gers aided it in 1999, completing the modern architecture. Between 2014 and 2017, LSTMs powered virtually everything sequential. Google's neural machine translation system used 8 stacked LSTM layers with 1,024 wide cells, reducing translation errors by 60%. Google Voice reported a 49% speech recognition error reduction using LSTMs. Facebook processed 4 billion LSTM translations per day. Apple's Siri, Amazon's Alexa, and iPhone's QuickType keyboard all ran on LSTM architectures. In 2014, Kyung-Yun Cho introduced the gated recurrent unit, a simpler variant with 2 gates instead of 3 and no separate cell state. GRUs are 26% smaller and 20 to 30% faster to train with comparable performance for most tasks. Then Transformers arrived and everyone assumed LSTMs were dead. But in May 2024, Hawkrider himself published XLSTM, accepted as a NeurIP's 2024 Spotlight paper. XLSTM-M7B, a 7 billion parameter language model released in March 2025, delivers performance competitive with Meta's Llama but with linear compute scaling instead of quadratic, potentially using dramatically less energy than Transformers. Sepp Hochreiter is staging a comeback at 60+, from 10 citations per year to 70,000 total, from obscurity to powering Siri, and now back to challenge the Transformer throne. LSTMs gave AI the ability to remember, and they're not done yet. But if LSTMs taught machines to remember sequences, the next architectures taught them to see. Convolutional neural networks. A feed-forward network trying to process an image treats every pixel independently. Show it a cat and it sees millions of unrelated numbers. Move the cat 2 pixels to the right and the network thinks it's looking at something completely different. This is why standard neural networks failed at vision for decades. Convolutional neural networks were designed for grid-structured data. Small learnable filters slide across the input, detecting patterns at every position. Early layers detect edges and textures. Deeper layers detect object parts and whole objects. This hierarchical feature extraction mirrors exactly how the human visual cortex processes information. 3 core operations make it work. Convolution, where a filter computes dot products at each position producing feature maps. Pooling, which downsamples by taking the highest value in a window, providing translation invariance. And fully connected layers at the end for classification. Parameter sharing means the same filter is used everywhere, making CNNs dramatically more efficient than fully connected networks. Then, in September 2012, everything changed. Alex Krizhevsky, Ilya Sutskever, and Geoffrey Hinton won the ImageNet competition with 15.3% top 5 error. The runner-up had 26.2%, a 10.8 percentage point gap. It wasn't even close. AlexNet had 60 million parameters trained on 2 NVIDIA GTX 580 GPUs, with just 3 gigabytes of VRAM each, less than most gaming PCs today. This single result launched the modern deep learning revolution. The race to superhuman vision happened fast. GoogleNet hit 6.67% error in 2014 with just 4 million parameters using inception modules. VGGNet reached 7.3% with uniform 3x3 filters. Then in 2015, Kaiming He's ResNet with 152 layers and residual skip connections hit 3.57% error, beating estimated human performance of around 5.1%. Andrei Karpathy, now famous for Tesla and OpenAI, tested himself on ImageNet and could only reach 94.9% accuracy with intense concentration. The machines had won. Today, CNNs are everywhere. Tesla's Autopilot uses ResNet-like CNN backbones, processing 8 cameras at 36 frames per second. Waymo explores over 10,000 CNN architectures via AutoML. Every smartphone uses CNNs for Face ID, portrait mode, and photo enhancement. Apple's neural engine runs billions of CNN operations per second in your pocket. Vision transformers dominate large-scale benchmarks with abundant data, but CNNs still outperform on small datasets and dominate edge deployment due to faster inference. Meta's Canva Next in 2022 proved that modernized CNNs with transformer-inspired design choices remain competitive. The future is hybrid. Here's what made it all possible. Fei-Fei Li built ImageNet by hiring 49,000 workers from 167 countries on Amazon Mechanical Turk to label 14 million images. It took the equivalent of 19 human years of nonstop labor. This boring dataset project is arguably what made the entire AI revolution possible. CNNs taught machines to see, but if you want machines to create, you need 2 networks fighting each other. Generative adversarial networks, 2 neural networks locked in a zero-sum game. The generator creates fake data from random noise. The discriminator tries to distinguish real from fake. Through adversarial training, both improve until the generator produces outputs indistinguishable from reality. Ian Goodfellow's own analogy: the generator is like a counterfeiter and the discriminator is like the police. Here's the origin story. On approximately May 26, 2014, Ian Goodfellow was at Les Trois Brasseurs, a bar in Montreal, at a going-away party. Friends were debating a generator network that would require gigabytes of data on GPUs, with only 1.5 gigabytes of RAM. Goodfellow proposed using a discriminator in the training loop. He went home. His girlfriend was already asleep. He coded for about an hour. It worked on the very first try, producing recognizable handwritten digits. His own assessment of those first images: they looked like crap. But we had been looking at crap from generative models for years, and we could tell that this was an exciting, new kind of crap. The evolution from blurry to photorealistic happened fast. DCGAN in 2015 added convolutional architecture for stable image generation. ProGAN in 2017 introduced progressive growing from 4x4 all the way up to 1024 by 1024. CycleGAN in 2017 did unpaired image translation, turning horses into zebras without ever seeing matched pairs. Then StyleGAN arrived in 2018. Photorealistic realistic face generation with disentangled control. StyleGAN 2 in 2020 eliminated artifacts, producing near-perfect faces. StyleGAN 3 in 2021 achieved alias-free generation at a cost of 92 GPU years and 225 megawatt-hours of electricity, enough to power 20 average US homes for a year, just to make AI-generated faces rotate more smoothly. This person does notexist.com launched in 2019 and went massively viral. Every page refresh generates a photorealistic face of a person who has never existed. It put GANs in front of millions of non-technical people. Facebook started taking down networks of fake accounts using GAN-generated profile pictures. Yann LeCun called GANs the most interesting idea in the last 10 years of machine learning. Applications went beyond faces. Deepfakes, super-resolution imaging, aging and de-aging actors in movies, medical data augmentation where patient privacy prevents sharing real data, drug discovery, fashion design, gaming textures. Then OpenAI's 2021 paper, Diffusion Models Beat GANs on Image Synthesis, marked a turning point. Stable Diffusion, DALL-E, and Midjourney all use diffusion, but GANs remain vital for speed-critical applications. A single forward pass generates an image versus the dozens of iterative steps diffusion requires. Ian Goodfellow went from coding GANs in his apartment in 2014 to becoming director of machine learning at Apple Special Projects. The GAN Zoo catalogs hundreds of name variants, a testament to the architecture's fertility. But if GANs are two networks fighting to create reality, the final architecture is one network that learned to talk to itself and ate the entire world. Transformers, a deep learning architecture that processes sequential data using self-attention, allowing every element in a sequence to directly attend to every other element simultaneously instead of the sequential processing of RNNs. Published as Attention is All You Need by Vaswani et al. At Google Brain on June 12, 2017, the Transformer is now the foundation of virtually all frontier AI systems. Self-attention works like this. When you read, "The animal didn't cross the street because it was too tired," your brain instantly connects it to animal. Self-attention does the same. For every token, it computes how much attention to pay to every other token using three vectors: query, key, and value. Multi-head attention runs this process multiple times in parallel, each head learning different types of relationships. Syntax, semantics, coreference. It's like a room where everyone can talk to everyone simultaneously, versus RN and S one by one whispering down a line. The title, Attention is All You Need, is a deliberate reference to the Beatles' All You Need is Love. The name Transformer was chosen because author Jacob Uskereit simply liked the sound of that word. An early internal design document literally featured illustrations of Optimus Prime. This paper, essentially named as jokes, now has 173,000 plus citations, placing it among the top 10 most cited papers of the 21st century. The scaling explosion created modern AI. The original Transformer had about 100 million parameters. GPT-1 in 2018 had 117 million and proved generative pre-training. BERT in 2018 revolutionized NLP, and Google adopted it for search in 2019. GPT-2 in 2019 hit 1.5 billion parameters and was initially withheld because the text was too convincingly human. GPT-3 in 2020 reached 175 billion parameters with few-shot learning, training costs around $4.6 million. GPT-4 in 2023 has an estimated 1.8 trillion parameters, passes the bar exam at the 90th percentile, and processes text, images, audio, and video simultaneously, from 117 million to 1.8 trillion parameters in 5 years, a roughly 15,000 times increase. Transformers do everything now. Every major LLM runs on them: GPT, Claude, Gemini, Grok, and Llama. Vision transformers challenge CNNs in computer vision. AlphaFold 2's Everformer predicted structures of 200 million plus proteins, more than experimental methods achieved in 60 years, and won the 2024 Nobel Prize in Chemistry. OpenAI's Whisper handles speech to text. The economic supernova is insane. ChatGPT reached 1 million users in 5 days and 100 million in 2 months, the fastest product adoption in human history. Netflix took 3.5 years, Instagram 2.5 years, the telephone 75 years. By mid-2025, ChatGPT processes 2.5 billion plus messages per day with 700 million plus weekly active users, nearly 1 in 10 adults on Earth. OpenAI's revenue grew from 3.5 million in 2020 to a projected 12.7 billion in 2025, a 3,628 times increase. The company's valuation passed $300 billion in March 2025. The generative AI market hit $62.7 billion in 2025. McKinsey estimates generative AI could add $2.6 to $4.4 trillion annually to the global economy. 92% of Fortune 500 companies now use ChatGPT, but attention is quadratic in sequence length. Very long contexts get expensive fast. This has spawned fund research into linear attention, sparse attention, and XLSTM alternatives. The environmental cost is staggering. Training frontier models requires millions of dollars in compute and massive energy consumption. Here's the final fact. Your brain runs on about 20 watts of power, like a dim light bulb. GPT-4 requires roughly 85,000 watts during inference, yet it can pass the bar exam in the top 10% while using 4,000 times more energy than your brain. The human brain remains the most energy efficient intelligence system we know of for now. If you enjoyed this video and want to see more, click the video on the screen now.